Hello, welcome to the course SJPHY3BO3 Electrodynamics 1. Contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. We'll continue to discuss topics from Chapter 1, Vector Analysis. In the last class, I introduced the polar coordinate system called spherical coordinates to you. The axes were r, theta and phi. If you recollect, r was the position vector, theta is the angle between position vector and the z-axis, and phi, the azimuthal angle, is the angle between x-axis and projection of the position vector on the xy plane. We have seen what's the relation between the Cartesian coordinate x, y, z and the spherical coordinates r, theta, phi. The unit vectors are r cap, theta cap and phi cap. If you notice, these three together form an orthogonal basis vector. So using this you can represent any vector as, for example, if you take a vector v, you can write it as vr r cap plus v theta theta cap plus v phi phi cap. We also derived the relation between r cap, theta cap, phi cap and the unit vectors in Cartesian coordinate system x cap, y cap and z cap. After that, we derived the infinitesimal displacement in the direction of r, theta, phi. Call it as dlr, dl theta and dl phi. Once you define this, you can derive the expressions for line element, volume element and surface element. What's remaining? The only thing remaining now is the vector derivatives. Okay, so we have three vector derivatives: gradient, divergence and curl, and a special operator known as Laplacian. Okay, let's start with the gradient. If you remember the Cartesian coordinate system, for a scalar function t, gradient of t is defined as dou t by dou x x cap plus dou t by dou y y cap plus dou t by dou z z cap. Now take the first term dou t by dou x. In using the chain rule, you can represent this in the spherical coordinate system as dou t by dou x equal to dou t by dou r into dou r by dou x plus dou t by dou theta into dou theta by dou x plus dou t by dou phi into dou phi by dou x. This is the classic chain rule. Okay. So you know how to write r, theta, phi in terms of x, y and z. So you can compute dou r by dou x, dou theta by dou x, dou phi by dou x. Do that. Then you have x cap, y cap, z cap written in terms of r cap, theta cap, phi cap. Okay. So you expand these terms also. Similarly, you do it for dou t by dou y and dou t by dou z. Okay. So I'm sure this is going to be a very tedious task. It may take you half an hour or 1 hour or so. This is a brute force method. If you want a simpler method, a more generic method, you can refer to Appendix A from Griffith's textbook. There he has given a general method for any polar coordinate system. Okay, you can do that. I'm not going into the details of those derivations. It's beyond the scope of our course. Anyway, I will give you the final results. I don't ask you to memorize any of these results. If you want, you can remember the first two. These two, the gradient and divergence formula, are relatively simpler. So if you want, you can remember this. Or using this tedious approach, you can derive on your own. Okay. Anyway, the gradient of t is defined as dou t by dou r r cap plus 1 over r dou t by dou theta theta cap plus 1 over r sin theta dou t by dou phi phi cap. Coming to divergence and curl, you have a vector function v equal to vr r cap plus v theta theta cap plus v phi phi cap. So divergence of v is defined as 1 over r square dou by dou r r square vr plus 1 over r sine theta dou by dou theta sine theta v theta plus 1 over r sine theta dou v phi by dou phi. Similarly, these two are the expressions for curl and Laplacian. So that's about spherical coordinates. Let's do a quick problem. Using spherical coordinates, check the divergence theorem for the function v1 equal to r square r cap using a sphere of radius r centered at the origin. Hope you remember the divergence theorem, which is also known as the Gauss theorem, which says volume integral of divergence of v d tau equal to closed surface integral v dot dA. Let's compute the volume integral first. For that, we need to first calculate divergence of v1. Okay. So remember the formula. Divergence is this formula. And if you look at our function v1, it has only r components. So essentially, you need to compute only the first term, 1 by r square dou by dou r square vr. Okay, so let's do that. So 1 over r square dou by dou r square into what is vr? Vr is r square. Okay, so 1 over r square 4r cube. So this is 4r. Now do the volume integral. The volume element d tau is nothing but dlr into dl theta into dl phi, which is r square sine theta dr d theta d phi. Multiply it with divergence of v1, which is 4r. Apply the limits. It's a sphere of radius r. So your r coordinate changes from 0 to r. Theta is the polar angle, changes from 0 to pi. And the azimuth angle always changes from 0 to 2 pi. Apply the limits, you get the value 4 pi r to the power 4. This is the left hand side. Coming to the right hand side, you have an area element and you have different combinations of area element. Which one do you choose? You need to basically look at the boundary. So boundary of the sphere. Basically, you are looking at the periphery of the sphere. So here, the radius is a constant, right? So your area element is determined by dl theta and dl phi. So correspondingly, dA equal to r square sine theta d theta d phi, and the direction is along the r direction. So take the dot product, r cap dot r cap. These two are unit vectors. You get 1. So you have r to the power 4 sine theta d theta d phi. Okay. So this is a double integral. You are integrating with respect to theta and phi. So r to the power 4 is a constant. Take it outside the integral. Apply the limits. And since you are integrating over the surface, the value of the radius is capital R. So once again, you get 4 pi r to the power 4. So you have proven that the divergence of theorem is valid for spherical coordinates as well. There's a homework for you. For the same volume, for the sphere of radius capital R, check the divergence theorem for the function v2 equal to 1 over r square r cap. So do the same procedure, you will find that the result is really intriguing. Okay, so that's a homework for you. So that's about the first type of polar coordinate system, which is the spherical polar coordinates. And the second type is known as cylindrical polar coordinates, or simply cylindrical coordinates. So here the axes are S, phi and Z. So this is the reference point P. S is the perpendicular distance from the Z axis. So this is the S coordinate. Phi, as usual, you take the projection of the position vector on the xy plane, then the angle between x-axis and the projection is the phi coordinate. Okay. So if you notice here, this is exactly similar to your x-axis. So you can call this as S, and phi is the angle between S and x-axis. Z-axis is similar to Z-axis of the Cartesian coordinate system. Now quickly write x, y, z in terms of S, phi and z. So I told you this is nothing but your S vector. So the x-axis is nothing but S cos phi and y-axis is S sin phi and z is z. You can also derive the converse relation. So look at x and y. Take x square plus y square. This is s square cos square phi plus s square sin square phi. S square is common. Take it outside. You have s square into cos square phi plus sin square phi, which is 1. So this is x square plus y square gives you s square, or s equal to square root of x square plus y square. Similarly, take the ratio y by x. So s and s are common, they get cancelled. You have sin phi by cos phi, which is tan phi, or you can write phi equal to tan inverse y by x. Let's take the unit vectors along the 3 coordinates. So unit vector along s direction, this is s cap. Look at the directions along the s vector. And the unit vector along the phi direction, this is phi cap. This is similar to your cylindrical coordinate. This is the direction, and you also have a z cap along the z direction. So just like r cap, theta cap, phi cap, or x cap, y cap, z cap, here also these 3 unit vectors form an orthogonal basis set, which means any vector v I can represent in terms of s cap, z cap and phi cap. So in general I write vector v equal to vs s cap plus v phi cap plus vz z cap. If you recall it, in Cartesian coordinate system you write the same vector as vx x cap plus vy y cap plus vz z cap. Okay, so the third component remains the same for both, only the first 2 components are different. So having defined a vector in the cylindrical polar coordinate system, the next task is to calculate s cap, phi cap and z cap in terms of the already known unit vectors, that is x cap, y cap and z cap. So you already know the drill, right? We have done the same procedure in the case of spherical polar coordinates. First, write the position vector r. So r is x cap plus y cap plus z cap. Expand x and y in terms of the cylindrical coordinates. So you get r vector equal to s cos phi x cap plus s sin phi y cap plus z cap. You know how to define the s cap and phi cap. S cap is dou r by dou s divided by modulus of dou r by dou s. Similarly, phi cap is dou r by dou phi divided by modulus of dou r by dou phi. So from this expression I can write dou r by dou s equal to cos phi x cap plus sin phi y cap plus, for the z component there is no s parameter, so this gets cancelled. So I have only 2 components. What is modulus of dou r by dou s? There is an easier way. You first calculate square of the modulus. This is nothing but dou r by dou s dot dou r by dou s. Take the dot product of this term with itself. Okay, you know how to do this. Just take the product of similar terms. So I have cos square phi plus sin square phi. This is equal to 1. So consequently, modulus of dou r by dou s equal to 1. Same way, calculate dou r by dou phi. So you have to find derivative of cos phi, which is minus sin phi. And here derivative of sin phi gives you cos phi. And the third component, there is no phi parameter, so the derivative of this term gives you 0. So dou r by dou phi equal to minus s sin phi x cap plus s of cos phi y cap. Calculate the square of the modulus. For that you take dot product of this with itself. So take the product of similar terms. First term will give you s square sin square phi plus s square cos square phi. square is common, take it outside, so you have s square into sine square phi plus cos square phi. The terms inside the bracket equal to 1, so this is s square, or modulus of dou r by dou phi equal to s. So once you know this, you can quickly calculate s cap and phi cap. So s cap equal to cos phi x cap plus sine phi y cap divided by 1, which is cos phi x cap plus sine phi y. Similarly, phi cap equal to minus s sine phi x cap plus s cos phi y cap divided by s. So this gives you minus sine phi x cap plus cos phi y cap. And z cap is nothing but z cap. The same way you can do the converse. You can represent x cap, y cap and z cap in terms of phi cap and s cap. You can do this as an assignment. Okay. Now we need to find out the infinitesimal displacement in the direction of s, phi and z. Call them as dls, dl phi and dlz. So this is the direction of s. So an infinitesimal displacement in this direction, you can call it as ds. This is the direction of phi, and this vector is nothing but your s vector, and the displacement in the direction of phi is nothing but this arc, which can be written as the radius vector s multiplied by the small displacement along the phi direction d phi. So this is s d phi. And the displacement along the direction of z is dz. So these are the displacement in different direction. So once you define this, you can derive the expression for the line element as dl equal to ds s cap plus s d phi phi cap plus dz z cap. For the volume element, d tau is nothing but dls into dl phi into dlz. This is s d phi dz. Similarly, you can also define the area element. As I said in the previous class, depending on the direction of the surface, the definition of the area element changes. So it could be a combination of any of these two. Okay. Looking at the limits, s is the distance between the z-axis and the point. So it changes from 0 to infinity. The azimuth angle we have seen in the last class changes from 0 to 2 pi because it varies along a circle. And coming to z-axis, you have all the ways from plus infinity to minus infinity. So these are the limits of your coordinates. Next is calculating the vector derivatives, gradient, divergence, curl, as well as the del operator. So do the same procedure as we have done in the case of spherical coordinates. First write gradient of t in terms of the Cartesian coordinate system. So dou t by dou x x cap plus dou t by dou y y cap plus dou t by dou z z cap. Using the chain rule, you can expand dou t by dou x as dou t by dou s into dou s by dou x plus dou t by dou phi into dou phi by dou x plus dou t by dou z into dou z by dou x. So you know s, phi and z in terms of x, y, z. From that you can calculate these derivatives. Also you know how to represent x cap, y cap and z cap in terms of the cylindrical polar coordinates. Okay, so you write that. Same way you calculate dou t by dou y, dou t by dou z. Just like the spherical polar coordinates, this is going to be a very tedious exercise. You can do it for yourself or by following the general method given in appendix A, you can get a more easy result. Okay. In any case, if you do that, you get the value gradient of t equal to dou t by dou s s cap plus 1 over s dou t by dou phi phi cap plus dou t by dou z z cap. Now if you choose a general vector v equal to vs s cap plus v phi cap plus vz z cap, you can derive the divergence as divergence of V equal to 1 over S dou by dou S, SVS plus 1 over S dou V phi by dou phi plus dou Vz by dou Z. Similarly, these are the expressions for curl and Laplace. So I'm sure it's going to be very difficult for you to remember all these equations. So at least remember the first two, which are relatively easier. So try to remember the gradient and divergence formula. Let's do a problem. Find the divergence of the function v equal to s into 2 plus sine square phi s cap plus s sine phi cos phi cap plus 3z z cap. So this is the expression for divergence. So you have to do dou by dou s of svs, dou by dou phi of v phi, and dou by dou z of vz. So let's do that. So this gives you 1 over s dou by dou s, s into vs, which is s into 2 plus sine square phi, plus 1 over s dou by dou phi of v phi. V phi is s sine phi cos phi. Similarly, dou by dou z of vz. Vz is 3z. Okay. So this is straightforward derivatives. You can compute this. So first term gives you 1 over s 2s into 2 plus sine square phi plus the derivative of second term is 1 over s into s cos square phi minus sine square phi, and derivative of 3z is 3. Now, so you have 4 plus 2 sine square phi plus cos square phi minus sine square phi plus 3. So you have 2 sine square phi minus sine square phi. This is sine square phi plus cos square phi. This is 1. So 4 plus 1 plus 3. This is going to be 8. So that's about the spherical polar coordinates. So essentially we come to the end of the chapter 1, vector analysis. If you look at the syllabus, there is a small portion left out. It's something to do with the Dirac delta function and some of the operators and functions related to Dirac delta function. So that portion will be done by Madhu ma'am. So in my next class, I will start chapter 5, which is magnetostatics. So I hope by then you will be thorough with electrostatics and electric field in matter. Then it is going to be very easy and straightforward for you to understand what's happening in magnetostatics. Okay. So see you. Goodbye.